Okay, so hi all and good evening and welcome back to the 11th week of TA live sessions for AI KRR. Before we begin, is my audio clear and is my screen visible?
Yes, sir.
Okay, thanks for confirming. So yeah, let's get started then. Like I've been saying in the previous few weeks, week 11 is also one of the relatively easier weeks of the course, and so it's highly encouraged that you try to uh, get the best score out of these assignments. Um, Also, like in the previous few weeks, there will be a lot of recall based questions from this week and some conceptual questions as well. So let's get started. So this is the first question in front of you, which says that, so Pam, you may have come across this in the lecture slides of week 11. Pam may try to explain an action mentioned in the story, and which of the following options do you think is relevant to this question? Pam explaining an action mentioned in the story. So which of these do you think would be the correct option? So I'll give you a hint. So if you go to the lecture slides on PAM, you'll find these three components of PAM written over there, right? PAM has three components: the predictive mode, the bottom up mode, and the incorporation component mode. In the predictive mode, a known goal predicts certain plans and actions, and in the bottom up mode, we recognize the plans a given action is a part of, right? So for a given action, from start from bottom and then see which plan it is a part of a given action. And in the predictive mode, it's like a top down approach. We start from a particular plan and then see what our actions can be put in that, right, from top to bottom. And then there is a third component called incorporation component, which builds the story representation. But actually, we need only just the first two components to answer this question. So given these two in mind, coming back to the question that we had, let's try to look at each option one at a time. Okay, so the first option says that in PAM, one may try to explain an action mentioned in the story by hypothesizing that it is part of a plan the actor is assumed to have. Now, which component of PAM this is most similar to? It is similar to the second component, right? Recognizing the plans that a given action is a part of. If you go back to the slides, it's telling us basically a similar thing, just phrased differently, right? By hypothesizing that it is part of a plan that the actor is assumed to have, right?
Yes, sir.
And if we look at the other component, predictive mode, which says that a known goal predicts certain plans and actions. Now, this is similar to option C, right? By matching it with an expectation generated by a known plan of the actor, right? So, here the plan is known and then the actions are generated based on that plan, right? So, these two options, options A and C, are the ones that have the closest similarity to the three components of PAM mentioned in the lecture slides. So if you have a look at the solution, actually these two are the only correct options, and then options B and D are not correct because they are not really relevant to the question asked here. So this is kind of a recall based question. Um, any doubts there, or should we move on to the next question?
No, sir. Go ahead.
Okay, great then. Let's move on to question 2 then. So now the question 2 asks us again about Pam, and it says that Pam may explain a plan that the actor is supposed to be using by which of the following. Okay. Maybe you can mute yourself. Yeah, thanks for that. So again, going back to the lecture slides, there's a very simple point in the lecture slides from using which this can be answered. So we'll have to look at the explanation process in PAM. Okay, so this is how it proceeds. In the first step, we see whether the event part, whether the event is a part of a known plan. If yes, then the plan is the explanation. If not, we go to step 2, which says that can a plan or plans be inferred from the event. If no, then we return a failure. If yes, then we go to the step 3, and then we proceed so on and so forth. So if you have a look at the different steps of the plan, the only thing that we are talking about are plans and goals, right? So these are the first 4 steps, and then these are the remaining 3 steps, steps 5, 6, and 7. Okay, so you can go through all of these steps as per your own convenience, but what we need to know is let's look at the options one by one and see which of these seem to be relevant to the different steps in the explanation process of PAM that has been mentioned in the lecture slides. Okay, so the first option says that it's knowledge of which goals are achieved by the plan. The second option says that by recognizing that the plan can be used to resolve a goal conflict. The third option says that by expanding the plan into constituent actions. And the last option says that by recognizing that the plan is used to resolve goal competition with another actor. If you have a look at the different explanation steps, you will see that nowhere there is a mention of constituent actions. Okay, while the other 3 options are somehow or the other mappable to the different steps of the explanation process. So based on that, which option do you think would be the incorrect one? I'll give a hint that there's only one incorrect option in this question. It will be option C, right? Because there is no place in which there is a mention of constituent actions, expanding a plan into its constituent actions in the explanation process. Okay, this is also kind of a recall based question. Okay, then let's move on to question 3, which asks us about the filler of a slot in an individual frame. And out of these options, we have to select which all are the possible entities that can be the filler of a slot in an individual frame. And again, this also has relation to some or the other lecture slide. So for this week and also the next week and some of the previous weeks, I'll recommend that topics that are more likely to have recall based questions, we just go through the lecture slides, go through each and every detail, and yeah, it's not possible to remember everything, but if you just kind of form like a basic set of notes, it should be easier to form, kind of answer these recall based questions. But coming back to the question at hand, let's see what answers do we have. Okay, maybe it's not present in this particular, it should be in frames. Okay, so this is that a frame is different from a script in that it is structured, it is a structured representation of with a collection of attribute value or slot filler pairs rather than chains of events conceptualizations. Okay, and these are some of the examples. It says that frames may be generic frames or individual frames, and the slots in frames can be of different types, right? Slots may have procedures attached. it can have a value, it can have a pointer to other frames. Now with this, so I think this is the key lecture slide that we will use to answer the question. With this in mind, coming back to the question, which options do you think would be the correct options in this case?
A and B.
A and B, okay. It can take a value, it can take a pointer to another frame. Let me go back to the slide. It also says that the slots may have procedures attached. So do you think
Option D is correct.
option D is correct? It can also be a pointer to a generic frame, right? Because if it can be a pointer to another individual frame, that individual frame might be a generic frame as well. So actually all options are correct in this case. Okay. So
Okay.
yeah, another example of a recall based question. Now we'll be moving on to slightly more conceptual based questions, and yeah, so let's move ahead. So now we come to inheritance networks, right? And this question asks us an inheritance hierarchy with a conclusion node C with respect to a node A, and then which of these options do you think would be relevant? Okay, so if you recollect inheritance networks from the lecture slides, using whatever you might remember, which of these options do you think would be correct? I'll give a hint. Remember when professor mentioned the concept of beliefs in inheritance networks, okay, and then use that knowledge to answer this question.
Option C.
Option C, okay. Okay, I'll say that option C is correct, but given that option C is correct, do you think any of the other options can also be correct?
Option A and B.
That's right. So it's a kind of a simple giveaway in that sense. Um, so in an inheritance hierarchy, if you might recall, we can have different beliefs. These beliefs can be contradictory, but they both can exist. Okay, it will lead to eventual contradictions that we will encounter when we go for further processing of inheritance networks. But if we just focus on the beliefs that can be inferred, then we can have both the conclusion that A is a C. We can also have a conclusion A is not a C, and then option C is just a restatement of options A and B together. And by default, if option C is correct, options D and E both become incorrect, or actually option D becomes incorrect. And for option E, actually we don't have enough information to say whether it can have or cannot have an admissible positive path or an admissible negative path. So we will go ahead and say that it is incorrect. So the correct options are A, B and C. Okay. Shall we move on to the next question?
Okay, sir.
Okay, let's move on to question 5 then. Now this might require a bit of thinking and processing. So question 5 is giving us a proper inheritance network or an inheritance hierarchy, which is given in this figure on the right hand side, and it says that use the following inheritance hierarchy to answer the questions in this group. Okay, in this group, in the sense, the next couple of questions. So we have to identify the edges that are admissible with respect to the node A in the above graph. Okay, A is the node at the bottom. This particular node over here. This is what we have to. This is going to be our point of view, and we have to select the edges that are admissible with respect to this node A in the above graph. Now, does anyone remember what exactly is the definition of an admissible edge in this inheritance hierarchy from the lecture slides? Anyone? If not, maybe we can have a quick look at these concepts. So first we need to know what is a positive edge and a negative edge. Okay, so an edge going from node A to node X without any cut in the arrow is called a positive edge, and it's denoted by A dot X. And the negative edge has a cut in the arrow, and it is denoted by A dot not of X. Okay, and a positive path is a collection of one or more positive edges, and a negative path is a collection of zero or more positive edges. So a single particular negative edge is also a negative path, and a set of positive edges followed by a negative edge is also a negative path, and it has its corresponding representations as well as given over here. Okay, now that we know what or how do we represent edges and paths, now let's look at when is a path admissible. So a path is admissible with respect to a node A, which is the point of view over here, if every edge in the path is admissible with respect to the same node A. Okay, this is a definition of an admissible path. Now to understand this, we need to know what is the definition of an admissible edge. So an edge is admissible, an edge, let's say from a node V to a node X, this is admissible with respect to the node A if some positive subpath starting from A with some intermediate nodes U1, U2, U3 up to UN up till V exists, and no subpath edge is redundant with respect to A, and the subpath is admissible with respect to A, and no node preempts the edge V2X. Okay, so this is kind of a heavy definition when you look at it, but we can break it down into several parts. Okay, so what we are trying to answer is whether an edge is admissible or not. Okay, this is what our main goal is. There are 4 conditions we need to check in order to say whether an edge is admissible or not. Okay, the first condition is some positive subpath must exist. Okay, in order for us to say that an edge V2X, this blue edge, can you see my cursor on the screen or is it not visible? Can you confirm?
Yes, sir, visible.
Okay, so if you have a look at this blue edge, either V2X or V2 not X, depending on whether it is a positive edge or a negative edge, both can be categorized as admissible edges. The first condition that we have to satisfy is that there has to be some positive subpath starting from A to V with some intermediate nodes U1, U2, U3 up to UN, and this number of intermediate nodes can be 0 or more than 0. Okay, that is the first condition. So is this condition clear? Okay, I'll assume it is clear. If there are any doubts, please.
Sir, if some positive subpath means that means all the path must be positive.
No, there must be
Path must
at
be
least
negative path.
there must be at least one positive subpath from A to V. That is what this condition says.
Okay, the negative path may be possible.
May be possible, but there must be at least one
Yeah,
positive
at least
subpath.
one positive subpath.
Yeah.
Okay, sir.
And then the second condition is no subpath edge is redundant with respect to A. Okay, we'll have a look at what redundancy is, but for now let's keep that in mind. Then we also have to check that the subpath is admissible with respect to A. Okay, so the subpath that we are considering, that recurrent in a recurrent relation kind of way, that itself has to be admissible with respect to A. Okay, and then the final condition is that no node in this set from A and the intermediate nodes till before V preempts the edge V2X or V2 not X. Also, we don't know till now what exactly is meant by preemption, but we will have a look at that. So these are the 4 conditions that we must check, And actually, if even if one of these conditions is not satisfied, we can say that the edge is not admissible. So we don't necessarily need to check all the four conditions when you are in an exam. Let's say, if even if one of these conditions is not met, you can straight away say that the edge is not admissible. Now let's have a look at what is redundancy and what is preemption. Okay, first let's have a look at what is preemption. So let's say there is this again this blue positive edge from V to X. If there is some particular intermediate node from A to V, and this intermediate node has a negative edge to the final node X, which is the opposite of the kind of edge that is there from V to X, right? So if V to X is a positive edge, then if there is a negative edge from an intermediate node Y to X, then that node Y preempts this particular edge. In case of a negative edge, if there is a negative edge from V to X, and if some intermediate node has a positive edge to the final node X, then this node preempts the V to not X negative edge. Okay, this is preemption. Any doubts in what
Sir,
preemption is? Yeah.
sir, is this condition valid for any intermediate edges as well, sir?
Uh,
For example, yeah. So here in the figure which you have shown,
hmm.
Vx comes at the end. Am I right, sir?
Yeah.
If Vx comes at the center,
Hmm.
and the same thing is happening, y negative edge to x
Uh-huh.
goes to it. Even then, we can
So
say that y preempts edge. Am I preempts the edge? Am I right, sir?
yeah, we can still say that. So basically, whenever you have to answer a particular whether a particular node is preempting a particular edge, you don't look at anything above that edge. You only look at anything below that edge.
Yes, sir.
So even if let's say, as of now in this graph, it looks like there is nothing above this X node, but there might as well be a set of other network structure above this X node, but we are not concerned with that as of now.
Yes, sir.
Um, but just because there is this node Y that is kind of negating or nullifying the effect of this V2X node, we can say that Y preempts the particular edge in consideration.
Yes, sir. Thank you, sir. Thank you.
Okay. So that was preemption. Now let's have a look at redundancy. Okay, so there are different ways of defining redundancy, but I find this particular way a bit more intuitive, so I'll just go through that. You can have a read through these definitions over here, but I'll just give an intuition. Okay. So let's say there is some inheritance hierarchy, and it basically goes from A and then some intermediate node B, T1, T2, Tm, up finally till W. Okay. What this basically says is that A is a B, B is T1, T1 is Tm, and Tm is W. Okay. So there is kind of this relation that keeps on defining what exactly the hierarchy or the inheritance structure is. Okay. If we already know that B is a T1 and T1 is a Tm and Tm is in turn a W, this already implies that B is a W. Do you agree with me?
Yes, sir.
So if we have an additional edge from B to W, this is not adding any extra information to our knowledge, the knowledge that we have, right? This is just a redundancy. Do you get the intuition?
So B to W path is the redundancy path.
Yes. So if I have to give an example, let's say that A represents a human being. Okay. So we can say A is a human being. Let's say B is a mammal. So we say that human being is a mammal. Okay. Now let's say that T1 represents the set of living organisms. Okay. So human being is a mammal. Mammal is a living organism. Okay. Then let's say Tm is something else. Okay. Tm, let's say, is resident of Earth. So human being is a mammal, mammal is a living organism is a resident of Earth, and then let's say W is an entity in the universe. So there is this particular inheritance structure. Now we already know, because of this flow of information, that a mammal is already an entity in the universe, right? So if we had an extra edge from this mammal to entity in universe, it won't add any additional information, it will just be redundant. So that is redundancy. But to confirm that this is actually a redundant edge, we also need to make sure that there is no particular subpath basically that so basically these edges that you see over here, these paths that you see over here, right, this coming from A and negating these each of T1 T2 up to Tm or even W, right, these negations must not be there for us to say that B to W is redundant. So this is an important condition.
Sir, can you please repeat the last part, sir?
Yeah, so let me actually try to explain it with an example. So let's say the lowermost node is that there is a human being called Ram. Okay, Ram is a human being. Human being is a mammal. Mammal is a living organism. A living organism is a resident of Earth. And then finally, resident of Earth is an entity in the universe. Okay, let's say this is our um, inheritance hierarchy. And let's say we added another edge from mammal to this one. Now this looks like this edge is not adding any additional information, right? Because we already know from this flow of information that a mammal is in fact an entity in the universe, right? Are you with me till this point?
Yes, sir.
Okay. Now let's say um, that there is some particular edge that goes like this, right, or a path that goes like this, and which basically says that a human being is not a living organism. Okay, because this path is present over here, we cannot say that this edge m to u is necessarily redundant, because there is a break in the flow of information because of this particular green edge that is there. So when we say that this edge m to u is redundant, we have to make sure that there is no other edges coming from here, let's say, that is breaking the flow of information in the usual direction. That is what I was saying about the other conditions mentioned in the definition. So is this a bit clearer now?
Yes, yes, sir. Thank you, sir.
Okay. So that was redundancy. And now coming back to admissible edges, so the four conditions now we understand is there should be no preemption, okay, as per this particular definition from A to the intermediate nodes. Um, the subpath should be admissible in turn. There should be no subpath S that is redundant, and there should be some positive subpath. So these are the four conditions that we have to check in order to know whether an edge is admissible or not. With this in mind, now let's come back to the graph that we had, and now I'll let you think over this graph for a couple of minutes, and then we can discuss which of these edges are actually admissible and not admissible.
So all are admissible except H.
Okay, So yeah, as one of your colleagues pointed out, actually all of these edges are admissible. Um, if you have a look at some of them or all of them in fact, so A to B, it's a simple edge, it's a positive edge, all the conditions are satisfied, it is an admissible edge. A to G, again a simple edge, it is also admissible. B to C, again a simple edge, again admissible. B to not E, again a simple edge, one hop edge, and it is a negative edge but it's still admissible. C to D, again a simple edge and all admissible. D to E, again a simple edge and admissible. And finally G to not C, negative edge but admissible. Okay. I hope this was clear. Should we move on to the next question? Okay, thanks for confirming. Let's move on to question 6 then. So in this, it's the same inheritance network or hierarchy that is given to us, but now we have to identify which of these edges are redundant with respect to the node A. Okay, so again I'll let you think over it for a couple of minutes and then we can have a discussion of the solution. I'll give you a hint. Only one option is correct.
H.
Okay, we have one vote for H.
H, sir.
So H is actually the correct answer. We just saw in the previous question that all of these edges are admissible and none of these also negate the redundancy condition. So all of these are actually non-redundant edges. Okay. Now the next question might be slightly more complicated. So here we have to identify whether the given paths are admissible or not. Earlier we were considering only edges. Now we have to look at whether the path is admissible, and in order to check whether the path is admissible, we have to remember the definition of the admissible paths that we just saw. Sorry about that. For a path to be admissible, every edge in the path should be admissible with respect to A. So given that, which of these do you think would be correct options? Again, I'll let you think over it and then we can discuss. Any partial solutions?
Except A, all are correct.
Okay, we have one vote for option, one vote
A
that
is
says
wrong.
that, yeah, that A is not admissible, right? So it is correct. Actually, A is actually not admissible, but I'll urge you to have a closer look at options E and F. Remember one of the important condition that we had to check there should be a positive subpath. There should be some positive subpath, right? This positive keyword is important.
That means, sir, if the negative path is present, then that will be not permissible. If
So,
the negative path is present,
hmm,
in case of C, option C, A to B, B to A is B, B is not E.
no,
So
see,
if the negative path is present, then that will be not permissible, sir.
no, see, that is the difference. So, in order for us to say that a particular edge is admissible, the subpath that comes from the start of the node and all the previous node, that should not have any negative edges. In this path A to B to not E, the subpath is A to B. That is the only subpath available to us, and that is positive. Do you get my point?
No, sir.
Okay, let me go back to the definition. In order for us to say that this edge v2x is admissible, the positive subpath must be from A till V.
B.
Okay, it's okay if v2x is negative.
Okay, B to X may be negative, but
May
A to B must be positive.
Yes, because that is the subpath that we are concerned with in this condition. That is what is differentiating options C and D from options E and F. So here the subpath is A to G
A
and
to
that is
G.
positive. Here it's A to B and that is positive. But here the subpath itself is negative.
A to G to negative. Okay.
Okay. And similarly here also A to G to not C to D, this also is a negative path. Because this
Sir.
is a negative path, E and F are not admissible. And A is not admissible because there is some redundancy. See here A to
Yeah,
B
A
to
to D.
yeah, A to D there is a redundant edge.
Okay.
So the admissible paths are B, C and D only. Okay.
Okay, sir.
Shall we move on to the next question then? Okay. I would let's move on to the next question then. So again the same inheritance hierarchy is given to us. Now here we have to deal with beliefs. Okay, remember I mentioned beliefs in one of the initial questions that we encountered. And this question asks us which of the following beliefs hold for the node A.
What is belief, sir?
Belief is basically your understanding of whether something can be another thing, right? Like if I mention, go back to this example here, we can say that Ram is a human being. That is a belief. Ram is a mammal. That is a belief. A human being is not a living organism. That is also a belief. So basically, these edges like A to sorry, these paths A to C or A to B. You remember one of the initial questions that we encountered. This one, A is a C, A is not a C. These are examples of beliefs.
Okay, okay, sir.
Okay, and that is represented by this arrow over here in this question. This A arrow E basically means A is a E. Okay, A arrow not C represents A is not
So
C.
the screen is not seeing, sir.
Sorry about that. Yeah, so I was just referring to this one, that this arrow A arrow E basically means that A is a E. Okay. And then A arrow not C represents A is not C. So these are the different beliefs that could be possible. We have to select the beliefs that actually hold true for this given node A. So which of these do you think would actually be correct beliefs?
Option E.
Option E. Um, so option E is actually correct, right? Because we can follow this particular path. Option E says that A is a D, and we can follow this path, right? Either we can go directly from A to D or A to B to C to D. So we can say that A is a B, B is a C, and C is a D. So by consecutive transitive relations, A is also a D, right? So this belief seems to be true. And remember what we discussed in one of the earlier questions, that there might be contradicting beliefs that could be true in the same inheritance hierarchy. So we have one vote for options A, B, and C, which says that A is a E, which is true, following the direction A, B, C, D, E, right?
And only option F is incorrect, I
That's right.
think.
That's actually correct. So let's have a look at all the options one by one to clarify. So the first option says A is E, which is true in this path, A to B to C to D to E. So A is a E. Option B says that A is not E, which is true in this path, A to B and then B to not E. Okay. Then the option C says that A is a C, which is true in this path, A to B to C. So A is a E. Option D says that A is not C, which is true in this path, A to G to not C. So following this path, A is not a C, which is contradictory, but it can still exist. Contradictory beliefs can exist. Option E says that A is a D, which like we saw just now, A, B, C, D. Through this path, it is true. But we do not have any evidence to support that A is not a D, right? Because there is no negative edge leading up to D, originating from A, or basically a negative edge that ends at D. Okay. So the only incorrect option here would be option F, and all other are possible beliefs. Is that clear?
Okay, sir.
Okay, that's great then. So yeah, that actually concludes all the questions we had for today. It's like I said before, it's one of the easier weeks, and most of the questions that we'll be getting are either recall based questions or such simple conceptual question based on inheritance hierarchy. So yeah, anything in particular that you would like to discuss, or else we can close the session for today. Okay.
Sir, if you can
Yeah.
just give a brief overview on PAM, goal, action, just a brief, it will be helpful for us, sir. Helpful for me.
Okay, I can try.
No,
Um,
at least the block diagram, flow
mhm.
diagram, it shows.
Maybe I can go through the explanation steps involved in PAM.
Yes, sir. Yes, sir.
Uh-huh. Okay, let's start with here. So this basically explains the basic algorithm, and this says that the input is a sentence that is read in the conceptual dependency. we You must recall conceptual dependency from one of the earlier weeks, right? if there is a from the previous discussions, you might recall that there are three components in PAM, right? The predictive component, right, which basically goes at in a top down approach, which given a plan, it tries to predict what are the possible actions that could be part of the plans, possible sub plans or sub goals or action that could be part of that plan. There's another component which is the bottom up mode, which starts from an action and then thinks about what are the plans that this given action could be a part of. Okay, and given these two components, there's a third component which basically builds the story representation using the first two components. Now coming back to the block diagram that we had, first we go to the predictive component. If there is a prediction that explains the given sentence that we use as an input, then we incorporate that input into our story representation. Okay, and then we go back to the same starting position to have a look at the next sentence. If that sentence is not explainable by the predictive component, we have a look at the possible actions available and see whether there is an explanation in which that action could be placed, some plan in which that action could find a placeholder. Okay, that will be a bottom up component. If we still can't find an explanation, then we say that the algorithm has terminated and we cannot incorporate this particular sentence into the story representation. If it does find a possible explanation in the bottom up component, we treat the inference as if they were a new input and then we go back to the starting point. So this is what the basic algorithm is. Now if we go back to the explanation step, go to the explanation step in PAM, this is what happens. So let's say we are talking about some particular event. Okay, the first thing that we'll check is whether this event is part of a already known plan. If it is a part of a known plan, then the plan is the explanation of the event and we add it to our story representation. If not, we go to step 2. Step 2 checks that whether a plan or a set of plans can be inferred from the event. Okay. If we can't infer, we will return a failure. If we can infer, we will then have a look at each of these individually and say that, and basically have a look at whether these plans can be the actual plans to be executed for one of the known goals. If yes, then again this is the explanation and we add it to our representation. If not, we go to step 4 and we check whether any of the goals can be inferred from these plans, right? And similarly, we keep on proceeding in a iterative fashion. Does that help slightly? Or
Yes, sir. Yes, sir. Yes, sir.
okay. So I'm not getting into the details of the rest of the steps. You can have a look at them. I suppose there should be an example as well. Yeah, I think this is an example. So yeah, you can have a look at this example as well. And the final story. Anything else that you would like to discuss? Okay, if not, then maybe we can close the session and then meet next week. So next week will be the last week of live sessions. There won't be any extra live session this time, but yeah, if you have any like the previous few weeks and today's week, I don't think it will take us a lot of time to cover the questions in the next week as well. So if you have any specific things that you would like to be discussed in the final live session, you please feel free to let me know through the discussion forum. Okay. Okay then.
Thank you so much, sir.
Okay, thanks all for attending and let's meet next week.
Thank you, sir.